Okay, we're going to work problem 8.16 now. This is asking about something called Hund's Rule, and how does this Hund's Rule affect the electron configuration of an atom of nitrogen. Now, this is not diatomic nitrogen, this is just one nitrogen atom and its electron configuration. So no bonds, just an isolated atom. So first off, what in the world is this Hund's Rule business, and how do we assign these electron configurations? Okay, well, Hund's Rule basically says that if orbitals of equal energy are going to be available to us, it's better to put electrons into the available equal energy orbitals in an unpaired way. Now we know that any given orbital can hold 2 electrons, but if we've got 2 or more orbitals of equal energy, we call that degenerate. It's better to put them in the orbitals unpaired. Okay, so to see what we mean by this, it's probably best to work an example. I've reproduced the box for nitrogen from the periodic table. It's atomic number 7. This is its molar mass. So because it's atomic number 7, we know it's got 7 protons in the nucleus, and in a neutral atom of nitrogen, it's got to have 7 electrons. So we have to assign locations or addresses to 7 electrons, okay? Now, if we do that, we first use something called the off-ball principle. This is also sometimes referred to as the building up principle, because what we do is we build up our atom from lowest energy orbitals to highest energy orbitals. So this off-ball principle is something a little bit different. That's how assigning electron configurations always really works, okay? We're going to go from lowest energy orbitals to higher energy orbitals. Now, it may be a little bit confusing what the order of orbital energies are, but I know your book has, there's a couple ways you can figure out. Your book's got a nice figure on this. It's on page 335. We'll call this the orbital energy figure. Basically, it lists orbital energies with respect to one another. But there's another way you can kind of get some hints as to what this ordering is. And it's actually to use the periodic table itself and think about what's an S block element, a P block element, D block, and so on. Okay, and I know there's another tutorial video about that. Now, if we look at this figure, we find that the lowest energy orbital possible for putting electrons into is always going to be the 1s. This is true of all elements. We always start there, the 1s atomic orbital. Now the thing is that this s orbital type can only hold 2 electrons. So we're going to fill it up completely because that's the lowest energy case. There's 2 addresses there, or 2 electrons can reside there. In this case, we've got 7 to assign. So we know that 2 are going to assign there. Now the next best place to put our electrons is the 2s. That comes next in energy. Again, any s-type orbital can hold 2 electrons. So we're going to put 2 there. Now that makes 4 total. We've still got 3 electrons to go. Now the thing is the next orbital in order of energy is the 2p. 1 doesn't have p orbitals available, just the 2, because of the rules for assigning quantum numbers. So we're going to put the remaining 3 electrons in the 2p shell for nitrogen. Okay, so we're gaining some traction here because we've now come up with the addresses, if you will, for where these electrons should be in nitrogen. But this doesn't necessarily answer the question about Hund's rule and pairing of electrons and how it affects the nitrogen. So to do this, I'm going to write this information in a slightly different way. What I'm going to do is I'm going to draw an imaginary energy axis here. And I'll call it semi-quantitative instead of imaginary, okay? I'm going to make a little box. And that box is my representative of my 1s orbital. Now I know I've got 2 electrons in there. So what I'm going to do is draw 2 arrows. 1 arrow for each electron. 1 arrow is pointing up, the other arrow is pointing down. The directionality of the arrow, whether it's up or down, represents that magnetic spin quantum number. So you might say m sub s of 1/2 positive is equivalent to an up arrow, and m sub s of negative 1/2 might be equivalent to a down arrow. Again, it's a little bit arbitrary, up or down, plus 1/2, minus 1/2, but you kind of get the idea. It's just to represent the spins, okay? Now, there are other orbitals, like the 2s level, so I'm going to draw a box for 2s. Now, this is higher in energy than the 1s, but nonetheless, it's the next best place for our electrons to reside. Now, following that, I've got my 2p orbitals, right? But the thing is how many different p orbitals do we have per primary quantum number? Isn't it 3? There are 3 possible 2p orbitals. And really for any, whether it's 2p, 3p, 4p, whatever, there's 3 possible orbitals that our electrons can reside in. So the business of this Hunds Rule business kind of gets into, well, I've got 3 electrons to put in these orbitals. How should I do that? Should I do 1, 2, 3? Or should I do it a different way? Okay? Now maybe I could do 1, 2, 3. So this Hunds Rule gets into the business of the very specific details of where we're putting our arrows in our boxes, or where we're putting our electrons in these orbitals. Now, these 2p orbitals we're going to consider to be degenerate. Degenerate is a kind of important word that you hear thrown around in this chapter. Degenerate. That basically means they're equal energy. So each p orbital has the same orbital energy. They're degenerate, we could say. So there's not really an advantage putting an electron here relative to here because they're kind of all the same. So this Hunds Rule business tells us that it's better to put the electrons in an unpaired fashion into degenerate orbitals rather than to pair them up. So the electrons do not pair until they're forced to pair, basically. Now, if I was to add another electron to my nitrogen to maybe make N- ion, if I make an N- ion, then I would have to have 8 electrons. Okay. Now, where's the next best place to put that next electron, that 8th electron? Well, it would be right here. I would be forced to pair up. And then if I added a second electron, it would go here. If I added a third electron, it would go here, and we'd fill up our 2p orbitals. But the idea, again, behind this Hunds Rule is that the electrons don't pair until they're forced to. Okay? That's the Hunds Rule. The off-ball principle, that's this building up principle. That's the idea that we're going to start at low energy orbitals, and we're going to work our way up, assigning addresses to the electrons as needed to complete the electron configuration for any element we want.